This is example 2.5. We're going to look at pressure on a submerged gate. Our case, the gate is 2 meters wide, and you can see a picture of it down here, right? This is our gate, and we now need to figure out what the reactions are at point A, where we have a normal force, and then of course we have a horizontal and a vertical force at B. So to start out, I'll draw a free body diagram. This would be our plate right here, our gate. We said we have our two forces down here, so we have maybe a B vertical and a B horizontal, and then of course up here we have A. Doesn't say anything about the weight of the gate, so we'll leave that out. So all that we're left then is the pressure of the water. Now, if we just want to sketch that in here, all right? So we know we'll have a distributed load on our gate from the water. It's not going to start at 0, so we can draw a little line here. And of course, we know as we're going down, it's going to get deeper and deeper. So we'll have something like this. Drawing a couple here. This will be our free body diagram. We can say that our pressure up here is going to be gamma times 1 meter, because it's 1 meter deep at A. And then at B, it is going to be 5 meters deep. So it'll be gamma times 5 meters. Now, to find our reactions, we of course need to get the resultant force of this load that we have. We can either do it for the entire trapezoid that we have here. It's easy enough to calculate, but of course for a trapezoid, it's a little more difficult to find where the centroid is. So we'll break this apart into a rectangle and a triangle. All right. So we'll have a resultant force from the rectangle. We'll call that PR, and we'll have one for the triangle. Fit that here somewhere. Call that PT for triangle. So maybe we'll figure out what these are first. So we can say the force from the rectangular part, right? So what is that going to be? It's going to be gamma times 1 meter. And that's going to be over the entire length of my gate. Now it's a 4-3 triangle, so that means 5 meters. And we know it's 2 meters wide. So that's all we have, right? So that then is 9,810 Newton per cubic meter. That'd be our specific weight. And then what do we have? We have 1 times 5 times 2 is 10. And meter, 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 so 10 meters cubed. We don't even need a calculator for this one, right? So that's then 98,100 Newton, or 98.1 kilonewton. Okay, that's the rectangular part. And then for our triangular part, we have a triangle, so we have 1/2. Then, so it'd be this piece here, right? So that piece there is gamma times 4 meters. On this drawing, at least a little different. It looks a little that this is smaller, but that's just a sketch. And then we know that also acts over a distance of 5 meters, and it's still 2 meters wide. So what do we get? We get, of course, again, 9,810 newtons per cubic meters. And then we get 4 times 5 is 20, times 2 is 40, divided by 2 is 20. So we get that times 20 meters cubed. And that is then 196,200 Newton, or 196.2 kilonewton. All right, so now we have our PR and PT. Of course, we know that that this distance here, like from the top to PR, that is because it's a rectangle, that's just half, so that would be 2.5 meters right there. And the same if we want to go all the way down to where our where the triangle is, right? So we know this is a triangle, so from the tip it'd be 2/3, right? So we have 2/3 from that upper direction, so that is then 5 10/3. All right. All right, so now we have all our distances set. Now we can start calculating stuff. Right, the first thing, so we want to find A and B, H and B, V. So I think the first thing that we'll do is we'll make a moment around point B, because the only unknown is going to be A. To do that, let's scroll down here. We can't get both on the same screen, but we can say that the sum of moments around B is equal to 0 is equal to, and then let's see. So we certainly have A. A is going clockwise, so it'll be negative, and the distance in height distance here, right, the vertical distance is what's interesting to us, that'd be the 4 meters. So we'd have minus A times 4 meters. The BH and BV, of course, go through B, so they don't have a moment arm. But then we can look at the PR and PT. PR is going counterclockwise, so it'll be positive, and it goes, if this is 5 meters, that's 2.5, so that's 2.5 left. So it'll be plus P rectangle times 2.5 meters. And then we have the triangle one, so if that was 10/3, then we're left with 5/3 for the rest. So that'd be, squeeze that in here, that'd be PT times 5/3 meter. Now, of course, calculate that out, but I like to keep that as a number for now. All right, so we're looking for A, so we can, of course, solve this for A. We can bring A on the other side and then divide by 4 meters. So we'd have PR times 2.5 meters plus PT times 5/3 meters divided by 4 meters. And that is then, we plug those in. We know what our PR and our PT is, and then we can multiply through, so we get 98.1 kilonewton times 2.5 meters plus 196.2 kilonewton times 5/3 meters divided by 4 meters. And that gives us 143.0625 kilonewton. I don't know if you round this to 3 different digits, 143 kilonewton. That's our A. Then what do we have left? So we have B, H, and BV. Now, if we did something, we do another moment somewhere, around moment on A, no, B and V both come in. So I think we'll just do vertical and horizontal force balance. So start with the vertical force balance. The vertical force balance, we have BV. A doesn't go in, and our forces here, like, we have to separate out, right? So we can do that into a vertical and a horizontal piece. something like this, right? And then we just have to look at where our angles are, or what our, but if we don't have angles, we have a ratio. We have 4 and 3 to 5, right? So we can see that. So we can see for the vertical part, we have the shorter ones. We have 3/5. So we can write our entire thing. I'm not sure why I'm still in red, but let's be consistent. So we can say the sum of forces in the vertical direction equal to 0 is equal to, we said BV is going upward. We don't have anything at A. And then both my forces are acting downward. So 3/5 times PR minus 3/5 PT. So that means we can solve this for BV. And what do we get? So we get, those are both negative, so they flip over. So we can say 3/5 PR, we said was 98.1 kilonewton minus 3/5 of 196.2 kilonewtons, and that is 176.58 kilonewtons, or 176 kilonewtons if we round it out. All right, so now we have A and BV, so we're left with BH. That's the horizontal components. We have A, we have BH, and then the horizontal components of the two pressure resultants. So we can say sum of forces in the horizontal direction is equal to 0, is equal to A minus BH times 4/5, minus BH minus 4/5 times PR minus 4/5 times PT. That means we can get BH is equal to, bring BH over, so everything here stays the same, minus 4/5 PR minus 4/5 PT. And we plug all those numbers in. 143.0625 kilonewton minus 4/5 times 98.1. 98.1 kilonewton minus 4/5 of 196.2 kilonewton, and if we calculate that out, we get minus 92.3775 kilonewton, or minus 92.4 kilonewton. And with that, we have calculated all of our reactions that we needed. Right? We have A, it's up here, BV, and BH. Right? All calculated.